Hello, algebra students, and welcome to the first video for lesson 3.6, talking about analyzing lines of fit. So we talked about lines of fit last lesson in terms of our linear relationships. So now we'll continue on and we'll analyze them. We're going to use the Desmos graphing calculator a lot today. So make sure you have that pulled up. It might be a good idea for you to stop and try these things on your own so that you can follow the steps along too. Right, and I'll try to write down the steps as we go through. All right, so let's look at question 1 here. So it says find the line of best fit. What is the equation of the line of best fit for the data? So this process is called a linear regression. So a linear regression is the method used to calculate that line of best fit, right? And again, it uses that trend line that kind of goes through most of the data. So we're going to graph this on Desmos, right? This table. And we're going to talk about how you do a linear regression through Desmos. So here is the link to Desmos right here. I'm going to click on it. We'll go there. So we'll probably finish this problem on Desmos. So I'll do some writing on here. All right, so the first thing we're going to do, I'll do it down here. So the first thing we do in Desmos is we need to add the table. So we're going to add a table. So to do that, you go up here to this plus sign and click table. All right, and now we're going to enter our data. So I'll enter the X column first. That's the top row of our table. So 1, 2, 5, 8, 9, 17. And then I'll enter the second column, which are the Y values: 30, 55, 75, 120, 145, and 250. Now you can notice that these numbers get kind of big, right? You can see that on the X and Y axis here, the numbers are small. So we can actually change the scale here using the wrench. So there's a wrench up in the top right corner. So we're going to use the wrench. And this will adjust our scale. Okay, so this will fix the scale of our X and Y axis. So the wrench. Okay, so if you click on this wrench here, so if you look at your x-axis right here, you can change its scale. It looks like 1 to 17, so let's go like 0 to 20, right? Make it kind of nice. And then your y-axis, again, positive. Let's go 0 to, let's go to 300. Okay, and if you take a look here, we can click and drag, but now you see your data, right? So here's our graph, right? And here's our points. So it might be helpful for you to take a, on your piece of paper there, right? And I'll draw it right here. So here's 0. This is 300. This is 20. And just kind of sketch this graph, right? So we have a point here, a point there, a point there, a point there, a point there, and a point way out there, right? You might want to just sketch that. And again, it's not accurate, but it's fine. And now number 2, we're going to type in a formula to get the line of best fit to do this linear regression. So it's going to be y1 squiggle mx1 plus b. Now to get the ones down here, you have to click the shift button and the minus sign. Shift and then the minus sign, the minus button. Okay, up there by the plus sign. So shift and minus will give you those ones. And then this squiggle is up by the number 1, right? It's a shift and the number next to the number 1 on your keyboard, top left corner, all right? This squiggle. So if I come here, so Y, I'm going to hold shift and the minus sign to get down 1. I'm going to arrow to the right. I'm going to hold shift and the button next to the 1 in the top left corner for my squiggle. MX shift minus sign 1, arrow to the right, plus B. And there I go. Now I'm going to erase my writing so that you can see what that equation is. All right, so be aware, it's going to go away. Right. So here we go. So here's your M value. Here's your B value. We're going to round to 2 decimals. So our equation for this line of best fit is y equals, our m is 13.5. This 8 makes that 5 become a 6. 13.5x plus, and this is 17.5, and that 8 rounds that 8 to a 9. There is our equation for this line of best fit. And you can see they graphed it And you can see how it kind of goes through the data, doesn't connect all the dots, but kind of just goes through. So there we go, line of best fit through Desmos. Okay. Next question, or next idea in our notes. Okay, so let's clear that. Okay, so understanding the correlation coefficient. So what does the correlation coefficient reveal about the quantities in a bivariate data set? So remember we talked about this idea of two variables, two quantitative variables. That's this idea of bivariate. So bivariate data set just means two variables, And we're going to look at what's called the correlation coefficient, right? This correlation coefficient is represented by the letter R. Okay, so it's right down here, right? The correlation coefficient, represented by the letter R, is a number between -1 and 1. And it indicates two things. It indicates the direction and the strength of a linear relationship. Okay? So there we go. So all that's here. So if we take a look here, we have a scatter plot with a line of best fit going through, and our R value is 0.984. So I'm going to drag this up here so we can write down. So what this means is, right, 0.984 is really, really, really close to 1. So this is a strong, because it's really close to 1, and because it's close to positive 1, it's a strong positive correlation. Strong positive correlation. And you can see that as x increases, y increases. Or I should say as x goes to the right. Let's do that. So as x increases, y increases. So let's do it like this. As x increases, y increases. And there we go. For this second one here, I'll change colors to blue. So for the second one, now you have an R value that's negative, but notice that it's not really close to -1. It's almost closer to 0. So this is a weak correlation. Right? And it would also be negative, a weak negative correlation. So it's a weak negative correlation. And then last but not least here, we have another line of best fit tightly going through these dots. So look at this, negative 0.995. That is a strong negative correlation. Strong negative correlation. So for a strong negative correlation, as x increases, your y is actually decreasing, right? They go in opposite directions. Okay, so there's our discussion on correlation. All right, now the last part of this video is on what's called residuals. Okay, let me bring this down here. So a residual is the difference between the y value of a data point and the corresponding y value from the line of best fit, okay, which we call the predicted value. All right, so here's your equation for a residual. It's the actual y value that happened minus the predicted y value. So if you look up here, right, so this point right there, that's the actual point, and this is the predicted. So to find the residual, you would take the actual minus the predicted, the red minus the green. This is actually going to give you, this black line is a positive residual because the actual point is above the blue line. Whereas down here, you have the actual value and the predicted. The actual value is below the blue line. So this would actually give you a negative residual. Okay. So again, the actual y value comes from the data point, and the predicted y value comes from your line of best fit. Now, once you get all your residuals, you can make what's called a residual plot. A residual plot shows all of these residuals. All right. And we are looking for a randomly distributed group of dots, because if that's the case, then your linear model is a good fit. And that's what you want. So notice here, notice that 0 goes right through the middle, and you have your positive numbers on the top and your bottom negative numbers on the bottom, right? You just want a random pattern of dots. You don't want them all above, you don't want them all below, just some above, some below, and that's your residual. So if you look here, right, okay, so let's call this the first residual, number 1. If you look here, the difference between 10 and 8 is a difference of 2. So this residual would be equal to the number 2. Well, look here, right? This is an x value of 6. So on your x value of 6, right, you have a residual of plus 2. This is representing this residual, right? Sorry, number 1. So this dot right here represents the residual from these two actual and predicted y values. If we come down here, I'll turn to blue. We'll call this number 2. So this residual, again, you're going from -3 and 3 and 5, but you would take 3 minus 5. This residual would be equal to -2, and it's at a y value of 4. So if you go to your y value of 4, look down here, really close to -2. This would represent that second set of predicted and actual values, that residual. Okay. Now, again, we're going to let Desmos do a lot of this for us. So the next example is going to show you how. All right, here we go. So it says student enrollment at Blue Sky Flight High School over 8 years is shown. The owner used linear regression to determine the line of best fit. The equation for line of best fit is the following. How well does this linear model fit the data? Okay, so we are going to do the following. All right, we're going to take this line and we're going to find the predicted values. But then I'm going to show you how Desmos can help us. Right. So number 1, let's find the predicted value. Let's show you how you find a predicted value. So to do that, we're going to take our x values and plug them in. So y equals -35. The first x value is 0 plus 1208. And if you were to do that in a calculator, you would get 1208. That is your first predicted value. So then to find the residual, you would take the actual y value minus the predicted value. So you would do, in this case, to find the residual, so then your residual would be 1235 minus 1208. And 1235 minus 1208 is 27. That would be the residual here at positive 27. Now, we could do that, but we're not. We're going to use Desmos now, right? So Desmos, if we enter the data, it does it for us. So that's what we're going to do, all right? So in Desmos, the first thing you have to do is you have to add the table. All right, so let's go do that now. And again, I'm gonna show you all this in Desmos, and we'll write on Desmos's screen. All right, so again, we're here. All right, so we're into the table. So we're gonna go add a table. Again, we're gonna let our x be years 0, 1, 2, 3, 4, 5, 6, 7, and these are years, just numbers, right? 0 through 7. Sorry. And then the students 1235, 1178, 1115, 1102, 1020, 1050, 1003, and 978, right? Okay, so that's the data, right? And once we get that, okay, once we get the table, I'll start writing. So we got the table. Now we're going to do our y1 squiggle mx1 plus b. Remember, shifts when you get the 1 and the 1 with the minus key, and then shift and the number to the left of the 1 to get the squiggle. All right, so here we go. So y, shift minus key 1, shift button to the left of 1, squiggle, mx, shift minus key 1, arrow to the right, plus b. Right? I'm going to erase the writing so you can see what we got. Right, and here we go. So notice here in this data, right, if I just stop and take a look, we have a lot of information here. Here is the correlation coefficient, right? Negative 0.9624. So if we bring in last problem, this is a very strong negative correlation, right? And then here is your equations for your m and your b for your slope-intercept form, right? And that's exactly what they got, right? Negative 35x plus 1208, right? That's where they got that equation from. But here's what I want to look at. I want to look at the residual plot. So if I click here, plot, there's the residuals. And again, remember the first residual was 27. Here's all the residuals. Our highest is a what? Our highest is a 26. Our lowest is the negative 47. These are all the differences between the actual y values and the predicted. Again, I didn't make you go through and find all the predicted values. So what we're going to do here is we're going to adjust the window, right? So once I click on this residuals button, which I did, it was the word plot, right? Once I clicked on that word plot, now we're going to find the wrench. We're going to adjust it. Now your x-axis can model the numbers here in the x. So we're going to go from 0 to 10, right? Because we're going 0. Now your y-axis, your smallest should be the smallest number over here, which is like negative 50. And your biggest should be around, we'll go 30. How about we just go 50 to make it even? Right, there you go. Okay, and here's your residual plot. And again, it might be a good idea to graph this. So if you just take a freehand graph, right? I'll do it right here, no big deal. Right, 0 in the middle. You're going to 50 up here, negative 50 down here. And again, you just kind of plot your points, right? So you have a point here, a point right there, a point down here, a point right there. At 4, it's way down here. At 5, it's around here. 6 here, and 7 there. So there's your residual plot, right? And again, what you're looking for is a random scatter. And I would say that these dots are randomly distributed, randomly scattered. So you would say because there is random, or the dots are randomly distributed in your residual plot, this means that the linear is a good fit. So this is a good model. Linear is a good fit. Okay. Again, as you take further math classes, maybe a stats class, you'll see there's also quadratic and exponential fits as well. Okay, but linear here's a good one. All right, I know that was a long first video. Sorry, the second video will not be quite as long, so stay tuned for video 2.